Two questions again. So we have here that we should show that for small damping, omega d, this is our damped angular frequency. This is our natural angular frequency. This is our damping force constant B. This is M, which is our mass, and this is K, which is our spring constant. So we are told for small damping, we should show that this is approximately this. So we are going to go by solution. By solution, we have that our damped angular frequency, omega d, is actually equal to the square root of omega naught square minus gamma square over 4, where we have gamma to be equal to B over M. So it means that our damped angular frequency omega b can be written as this, the square root of omega naught square minus B square over 4M squared. So that is our damped angular frequency. So let's see how we can make this expression to look like this. So the first thing I want to do is to factorize omega naught from this expression. So I can have our damped angular frequency omega d to be equal to the square root of omega naught square into bracket 1 minus gamma square over 4 omega naught square. So I can have this expression. So I'm using this part because I don't want to be walking around with B and M everywhere. So what I did from here, I just factorized omega naught square from this expression. So I factorize it out, here becomes 1, and this should come under here, so that when this multiplies back, it can still cancel from here. So that's going to be omega d. So let's move forward. By using the idea of surd, this is equal to square root of omega naught square times the square root of 1 minus gamma square over 4 omega naught square. So that's what we are going to have. And of course, our damped angular frequency omega d will become omega naught square root of 1 minus gamma square over 4 omega naught square. So that's what we are going to have. So since they said small damping, since we have small damping, we'll have this limit that gamma should be gamma over omega naught is going to be much less than 1. So this is for small damping, since we are talking about small, very small damping. So small damping, we're going to have this as what should lead us. Now, if gamma over, why? Because actually for small damping, gamma is going to be less than omega naught. So if gamma is less than omega naught, so gamma over omega naught should be far less than 1. So if we use it here and apply the binomial expansion for this radical, so if we apply the binomial expansion approximation for this radical, we have that from binomial expansion, so for the binomial expansion, we are going to have that a square root of 1 minus x squared should be equal to 1 minus x all over 2. So that is the binomial expansion. That's the binomial expansion. Sorry, not square root of 1 minus x squared. I want to say the square root of 1 minus x. So the square root of 1 minus x should not be equal to, but rather it should be approximately equal to this, approximately 1 minus x over 2. So in other words, we can say the square root of 1 minus gamma square over 4 omega naught square should also be equal to, so what is it going to be equal to? It's going to be approximately 1 minus gamma square over 8 omega naught squared. So it's going to be approximately this. So if we apply mathematics here, we're going to have, let's bring back our gamma, what gamma is, which is B over M, and let's bring back what our omega is. You're going to have this is equal to 1 minus, so gamma is b square over m square all over a times omega naught square is k over m. So that's it. So if we expand that, we are going to finally have it's equal to 1 minus b square over, so m, we cancel one m out of here. Why this m is coming down? So 8mk. So finally, our damped angular frequency is going to be approximately equal to omega naught times 1 minus b square over 8mk. So it is quite easily done. All right, see you on the next question. So, want to solve this question again? Call it question 2, same on part 2 DHM. So you have to show that the time elapsed between successive maximum displacement of a DHM is given by 4 pi m divided by the square root of 4km minus b square. So this is what we were given. So by solution, this time elapsed between successive maximum displacement is actually our damped time. So T of D, damped time is 2 pi over omega D. Remember that formula for period, T is 2 pi over omega. So I just added the D to show it is damped. So TD is 2 pi over omega, and we have omega of D to be square root of omega naught square minus gamma square over 4. So what we just have to do is to make this expression to look like this, and we are good to go. So TD, the damped time, TD, damped period, is 2 pi divided by omega naught square is k over m, and gamma is b over m, so b square over 4m square. So it means this expression is going to give us that expression. So from here, we can perform algebra, and we're going to have 2 pi square root of 4km minus b square all over 4m square. And of course, by sword, the square root of 4m square should go up. So TD is 2 pi times the square root of 4m square divided by the square root of 4km minus b square. So finally, if we take the square root of this, it's going to give us 4mk divided by square root of 4mk minus b square. So it is quite easily done as seen. So the same expression, not k please, this is pi. So 4m pi please, 4 pi m divided by square root of 4km minus b square. So see you on